this is also very important theorem. A mapping F of a matrix space X into Y is continuous if and only if F inverse C is closed in X for every closed set C in Y. If I take the complement of this closed set C, then it becomes your open set, and let me name this as V. So I can rewrite this statement as a mapping F of a matrix space X into Y is continuous if and only if F inverse V is open in X for every open set V in Y, right? And that open set is the complement of this closed set C. Is it fine? Okay? Alright. So suppose F is continuous in X and C is closed set in Y. We have to prove that F inverse V is open set in X, as I have taken this closed set to be as the complement of C, that is equal to V, and that becomes the open set in Y. And for this open set in Y, I have to prove that its inverse is open set in X, that is the inverse of V, right? Where the complement of closed set C is taken, and that is named as V, which becomes your open set in Y. So for this open set in Y, for every open set V in Y, we have to prove that F inverse this open set, that is V, F inverse V is open set in X, right? So to prove that F inverse V is an open set, let's take one element from F inverse V, this open set, right? So let me take that P is the element from F inverse V. Then F of P belongs to V, right? Because V is open set in Y, so FP is an interior point of V. So therefore, FP is an interior point of V. Now if FP is belonging to V as an interior point, now when the point becomes the interior point of the set, if its neighborhood is a subset of that set. So if FP is the interior point of V, then its neighborhood also belongs to V, that is, it becomes a subset of V, right? So for the neighborhood, there exists epsilon positive such that the epsilon neighborhood of FP is a subset of V, right? Why I have taken here epsilon, why not delta? Because the neighborhood of FP is a subset of V, and V is the open set in Y. Please remember, whenever we are talking about the metric space Y, we have to take the epsilon neighborhood. And for the metric space X, we have to take the delta neighborhood. Please remember this important point. So because this neighborhood is a subset of V, so I have to take epsilon positive for this neighborhood, right? Now since it is given to us that F is continuous at P, so by the definition of the continuity, therefore there exists delta positive such that the metric distance of f of x and f of p is less than epsilon in Y for the metric distance between xp is less than delta in X, right? For the metric distance less than epsilon, this means that fx is belonging to the neighborhood of fp, right? So this f of x is belonging to the neighborhood of fp. And because this metric distance is in Y, so for Y I have to take the epsilon neighborhood for x belonging to the neighborhood of P, that is the delta neighborhood, right? So x belongs to the delta neighborhood of P. Fine. Thus, x belongs to the delta neighborhood of P implies fx belonging to the epsilon neighborhood of fp but epsilon neighborhood of fp is subset of V. So this implies f of x belongs to V, which further implies x belongs to f inverse V. So from where the x has been taken? From the delta neighborhood of P. And where we have reached that this x belongs to f inverse V, which means this neighborhood is a subset of f inverse V. So this implies delta neighborhood of P is a subset of f inverse V, right? So therefore, because the neighborhood of P is a subset of f inverse V, and when the neighborhood of the point is a subset of some set, then that point becomes the interior point of that set. So therefore, P is an interior point of f inverse V. But P was arbitrary. So therefore, every point of f inverse V is an interior point of f inverse V. This point P is from, yes, from where I have taken this point P? F inverse V, and P was arbitrary. So therefore, every point of f inverse V is an interior point of f inverse V, right? So as P is belonging to f inverse V, and P is also arbitrary, so this means every point of f inverse V is an interior point of f inverse V. So one way of the proof is done. Now the other way. So conversely, suppose f inverse C is closed in X for every closed set C in Y. We have to prove that f is continuous on X, right? Let's take one point from X. Let P belongs to X, right? Then, because f is a mapping on X to Y, the metric space X to Y, then f of P belongs to Y. Yes? Okay. Now for a point that belongs to the metric space Y, its some neighborhood also belongs to Y. Yes? We can define its neighborhood that should belongs to Y. So defining its neighborhood, therefore, for epsilon positive, because we are talking about the metric space Y, so I have to take the epsilon neighborhood. So for epsilon positive, the neighborhood of FP with the radius epsilon belongs to Y, right? Now, the neighborhood itself is an open set. Let me name this as V, right? So this open set V, being a neighborhood, is open set in Y, right? Because every neighborhood is an open set. So if I name this neighborhood to be as V, then this V is open set in Y. Verify? Alright. Now if V is an open set in Y, can I write its complement is closed in Y? Yes? Which further implies by hypothesis, because it is given that f inverse C is closed in X for every closed set C in Y. So here the closed set in Y is V complement. So by hypothesis I can write that f inverse V complement is closed in X by hypothesis, right? Please note here, f is a mapping from X to Y, then f inverse is a mapping from Y to X, right? So this f inverse Y belongs to X, right? Which can also be written as further that f inverse V complete complement is closed in X. Which means F inverse V is open in X. Now F inverse V is open in metric space X. Let me take one point from this open set, and we have to prove that F is continuous on X, which means first I have to prove that F is continuous at this point P. So let's suppose that P is belonging to this open set F inverse V. Because it is an open set, and a point belonging to open set means that point is an interior point of the set. So therefore, P is an interior point of F inverse V. Being the interior point, its neighborhood becomes the subset of F inverse V. So let's take the delta neighborhood of P, right? Why delta? Because we are in the metric space X, and for X we always take the delta neighborhood. For Y we take epsilon, right? Please remember this. So thus, there exists delta positive such that the delta neighborhood of P is a subset of F inverse V. Therefore, if I suppose that X belongs to this delta neighborhood of P, this implies X belongs to the F inverse V open set, right? Which further implies F of X is belonging to V. And V is nothing but the epsilon neighborhood of Fp from here, right? So this V is epsilon neighborhood of Fp, which implies this Fx belongs to the epsilon neighborhood of Fp. So Fx belongs to the epsilon neighborhood of Fp, which further implies, from here I can write the metric distance of Fx, Fp is less than, because it is epsilon neighborhood, so it is less than epsilon in Y. For the metric distance of Xp less than delta in X, right? So this implies the metric distance of Fx, Fp is less than epsilon in Y for the metric distance of Xp is less than delta in X, but epsilon was arbitrary. In the definition of continuity, we write further that F is continuous at P, but P was arbitrary, right? And to where P is belonging? P is belonging to X metric space, right? And P was arbitrary, which means if F is continuous at this point P and P was arbitrary, any point in the metric space X, then we say that F is continuous on this whole X metric space. So therefore, F is continuous on whole X, the metric space X, right? So here ends up the proof. Alright, thank you, stay blessed.